Thank you, Julie. And since I'm the first one, I'll just go ahead and say that I'm a little bit sheepish to be listed as a co-organizer for this and actually be the first. I did not put myself as first here, so please remember that. The people who get the credit here are Julie, and particularly Eric Parker and Jamie Elsa Cook, Jose Aponte, and a few others. They're listed somewhere in the program, and I'm afraid that I was not very valuable to the team about contributing, but they let me talk anyway. Anyway, I'd like to talk about something fairly simple, actually, aliphatic compounds. This is a group of compounds that are, generally speaking, not nearly as well studied as some of the aromatics that you heard about yesterday, and a number of the aromatic speakers, or their compounds are aromatic, who were sitting here yesterday, some of those people. And so this is a different group. So if you're not familiar, I'll show you a picture here in a few minutes. The other aliphatic, the other cyclic organic compounds, and in case you don't know me, let me just say that let's see if this works. Yes. We have a laboratory at the Goddard Space Flight Center. This could be pictures of any place. This could be pictures of University of Washington, but trust me, this is from near Washington, D.C. This is actually our laboratory, not just any generic pictures from Wikipedia. And we do three things. We do planetary science, we do some interstellar chemistry, interstellar astrophysics, and we do astrobiology. So over the 15 years or so we've been involved in NAI, astrobiology has been a wonderful way to tie together those two end members, two extremes there, planetary science and interstellar chemistry. So thank you very much. I'll give the commercial right here for the NAI and the Goddard Center for Astrobiology. The things we study tend to be cold. We think of ourselves as going from Mars outward. You know, the temperature of Mars is a little bit high on our range of the thermometer, and we go outward toward I guess we've done a small amount of Mars. We've done a small amount of Jupiter, a small amount of asteroids, and going out really toward Europa and Pluto and the interstellar medium and cometary ices. So this is sort of range we're talking about. So almost everything, whenever I give a talk, it's focusing on the solid phase as opposed to the gas phase. And I don't think in 30 years or whatever it's been, I've ever talked about the liquid phase. So I'm not going to talk about comets striking the ocean or something like that. So here we go. If you've taken organic chemistry, you've seen this before, or if just been around the block, you've heard of aromatic and aliphatic compounds. So aromatics are there on the left. The famous benzene ring was isolated by Faraday and worked out by Kekulé somewhere in the 1800s. And at the bottom there, one of the Erlenmeyer men, I've forgotten which Erlenmeyer it was, but one of the Erlenmeyers worked out the naphthalene down the bottom left. If I can point this down here, you've heard of these. And these are interesting, of course, but for astrobiology, maybe these are even more exciting. The nucleobases that you find inside of you right now, nucleobases are aromatic flat compounds that have this so-called delocalization. These lines here, in case you've forgotten, these mean extra electrons, 2 extra electrons for every extra line there. So these are well studied. There are lots of work finding these things in meteorites, looking for these things in interstellar space, studying these things in the laboratory, studying these, of course, in vivo, lots of work and so forth. In contrast, these have been not nearly as well studied, the ring compounds on the right-hand side there. And part of the reason is that I'm a chemistry person, and the chemists tend to have a little bit of a bias against these things over here because of the way that they're bonded together here. The sort of natural bonding that you find for carbon is bond angles like 109 degrees or 110 or 120 and occasionally 180. But once you start getting to bond angles like 90 degrees with the carbon, the square, and the triangle of 60, the molecule's just not happy. And we know this because of a man named Adolf von Baer, who got the Nobel Prize for working this out over 100 years ago, who told us that these molecules are what he called strained. If you look at these the wrong way, they begin to react and to break apart and to isomerize and things like that. None of these compounds like this are sort of saturated compounds, have all the 4 bonds taken care of with 4 atoms. And none of these things are really known, definitively floating around the interstellar medium. Still looking for these things. And I'll come back to that before we're done. Just because we have a little bit of a bias against these in our minds and as a chemist doesn't mean that nature has a bias, because you do find that these things are out there in nature. And I never really knew this until about a year ago when we had a student working on this. And she went to an old-fashioned library and found some old-fashioned books. And actually, books, it's one of those things we used to have before we had the internet. And she found that there are natural products that you have in nature, natural products in nature, that have these three mirrored rings. And there's a triangle here and a triangle over here somewhere, and amino acids, steroids, and so forth. And I never knew this. I never knew that you had cyclopropyl rings just kind of floating around us. I thought this is something you bought from the Sigma Aldrich Chemical Company and so forth. But it turns out there are natural products. Nature is not as biased against these as maybe we ourselves are sometimes. And so we began to wonder what it is that's known about this from the point of view of low temperature chemistry, and why haven't we found some of these things in interstellar or cold environments. And we looked in the literature and we found that one problem is a lot of the things we'd like to know about these things just are not have not been studied. Just things like, how do you make these in cold environments? There's a little bit of work on that. Fundamental properties of some of these molecules. Stability in radiation environments. Radiation is essentially everywhere. Once you get below a meter or so on Europa, you still got, you got to worry about radiation once you get, unless you're a meter or so below. Reaction chemistry, lots of liquid phase chemistry, gas phase chemistry by chemists, but solid phase chemistry, lots of cold environments in space. This sort of work just hasn't been done. So I'm going to blast through a few simple things here, and then I'm going to stop and we'll go to the next speaker. So here are a few things. Synthesis. Okay, sometimes we get the idea that these meetings that chemistry started or astrobiology started in the year 2000. It did not. This first reaction up here is a century old. This is called, what's this called? Anybody know? Shout it out if you know what the kind of reaction this is. What? Epoxidation. It's an epoxidation reaction. It goes back at least 100 years. I don't know. The Ukrainian Journal of Chemistry, I think it was, reported the first instance of epoxidation long ago. So this is not unusual, but there have been people like Patrice Cole up here, my French colleague here, Julie, you saw that. Patrice Cole has studied this in the simulated Titan atmosphere and found that there's just a little bit of oxygen. Then you can have hydrocarbons capturing the oxygen in Titan's atmosphere and starting to make rings like this as ethylene oxide. And the same type of reaction here, this is CH2, carbene chemistry, methylene. You can make these same sort of triangles here. This is not new. This is really old stuff. And so for that reason, we've not devoted much time to it. It's all in the literature. See me, I'll give you the references. It's easy to find. If you have hydrocarbon deposits on Pluto, and you do, hydrocarbon deposits on Pluto, you're going to get this sort of chemistry over here. It's just you can't stop it. That's one of those things. So we went on, looking at other types of molecules with this ring structure here. Here are 5 that have the cyclopropyl ring structure and two ethers over here. These 2 are known as interstellar. We recorded infrared spectra of these things. Most of these things have never been recorded. There's some very nice isomerization processes that you can see up here, conformational changes that you can study. I'm not going to talk about that. But instead, just saying something as simple as what's the index refraction of cyclopropane solid. I don't know why anybody would ever want to know that, but we did. We wanted to know what's the density of solid cyclopropane. And so you go out and try to measure these things, or try to find these things in the literature, and you're just out of luck. So if you study this sort of stuff, what do you do? What you do is you look up what the liquids are like. Use liquid phase data instead of solid phase data. So liquids are here on the left, on the vertical, and the horizontal is ices. And if you can see a correlation there, please see me, because we probably have a job for you later. I cannot see a correlation to any of that. It looks like, one of these things where my children would take a paintbrush and throw it up against the easel, splatter or something like that. And so you wonder about the validity of your measurements, if this is what you're getting. Do we waste our time for a month trying to do all this sort of stuff? But there is a way, believe it or not, that you can combine these 2 things here and start to check to see if you've done your job well, see if you've made and you have to be over 55, I think, to understand this. It's a property called molar refraction, which is hardly ever taught anymore, molar refraction. It's a way that you can combine these 2 things together, which looks like nonsense, and come up with something that seems to make sense. And so here it is. Even if you've never heard the words molar refraction before, I hope you'll be impressed by that straight line. The straight line everybody likes. And this is just something that's not taught very often anymore, the molar, except maybe to engineers and some material scientists. So we're very happy when we got this. This told us that we were measuring these things properly. Molar refraction of a solid versus liquid, we get a nice pretty straight line. That's one example of what we call a fundamental property. Here's another property that's more related to astrobiology. is stability in radiation environments. We measure how fast these molecules are destroyed if you expose these to ionizing radiation at a low temperature. And I've just picked 6 molecules up here. The stars with cyclopropane, the mother of all these things, the parent, the archetype. And then cyclopropane here, if we let ethylene oxide, just give it a number 1 to normalize everything. And what this means is it takes 32 times as much radiation to destroy half your benzene sample as it does the ethylene oxide. And so the important part here is that cyclopropane is not, on the extremes. It's in the middle here somewhere. All these other things have been found in various places in extraterrestrial environments. Ethylene oxide, propylene oxide, first chiral molecule found in space a few years ago, in space, remote radio telescopes. So cyclopropane is sort of in the middle. And if you want their actual data, don't go and hack JPL or Goddard or anything like that. Just ask me. We'll give it to you. We don't have any secrets here, anything like that. Just ask us and we'll give you the data. We can tell you sort of a rough idea. How long will one of these molecules, these 3-membered rings, hang around in Europa? Not long. We're talking about years here. NASA wisely does not let me speak officially, but unofficially, as a scientist, I would say that you need to dig down a meter or so before you really get to the good stuff on a place like Europa. The radiation is going to tear you up on the surface. The interstellar medium, these things last a long time, millions of years, but it's going to be a long time before we get to the interstellar medium, flying, space travel. Here's the trick the radio astronomers use when they want to find something that has no dipole moment. Nice, beautiful, symmetric molecules like benzene. What they do is they stick a CN group on this thing. This gives it a whopping dipole moment. It's like a flag, waving the flag. Here I am. And so what we propose is the same sort of thing. If you want to find cyclopropane, no dipole moment, what you do instead is you look for something, a derivative of it, a cyano group here. And so naturally we have to see what sort of reactions that thing will undergo. And so here's one radiation. This has been known since, I guess, the 1930s. This thing isomerizes. This is some work I did with Marla Moore some years ago. But this one does the same thing. We've measured this reaction. We've looked at this. Hope to publish this in the next few months. And so you get a nice isomerization. This is a place I will invite collaboration because this stuff smells awful. It is like, what's the words? Foul, those old literature papers, foul, evil, all those words like that. It smells terrible. But you really do get this sort of isomerization. Maybe that's not important. What's important is that it doesn't just fall apart. That you do get these rings with a certain stability, the same sort of stability that you find with molecules that are already known to be interstellar. Julie, how are we doing for time? We're about done? Okay, so let's just wrap it up very quickly. What have we done? We took a simple molecule here, cyclopropane and some of its derivatives. And we measured some physical properties. We've got IR spectra at low temperatures. We can actually study these things in a laboratory. We can quantify the samples now. 6 months ago, I couldn't do that. We measured stabilities, looking at reaction chemistry, and we've got a search strategy for you. So what I've been saying for about 6 months now is seek and you shall find some rings. So thank you. There's nothing here that's sacred. Take all the pictures you want. Ask anything you want. Thank you very much.